बिस्मिल्लाहिर्रहमानिर्रहीम औज़ुबिल्लाहि मिनश्शैतानिर्रजीम बिस्मिल्लाहिर्रहमानिर्रहीम इक़रा बिस्मि रब्बिकल्लज़ी खलक़ खलक़ल इंसान मिन अलक़ इक़रा व रब्बुकल अकरमुल्लज़ी अल्लम बिल क़लम अल्लमल इंसान मा लम यअलम। ये जो पहली आयत है कुरान की, इसमें अल्लाह ताला ने इल्म को बहुत अहमियत दी है और कहा है कि अल्लाह ताला की ज़ात वो है जो उसने इल्म दिया इंसान को, जो कि उसके पास नहीं मौजूद था। और बहुत सही और जगह पे भी ये बात आई है कि अल्लाह ताला के पास सारा इल्म है और उसमें से थोड़ा सा हिस्सा मिलता है और कभी हमें कंप्लीट नॉलेज तो हो ही नहीं सकती है। तो इसमें यानी हमें एक सबक है कि एज अ स्टूडेंट हम लोग यानी कभी ऐसा मुकाम नहीं पहुंचेगा कि हम सब चीज़ जानते हैं, बल्कि हर वक्त हमारी नॉलेज इम्परफेक्ट ही रहती है और बहुत यानी थोड़े यानी जैसे कि जितना आदमी ज़्यादा सीखता है उतना उसको ये समझ में आता है कि मैं कुछ भी नहीं जानता। और इसके बरअक्स जो गुरूर है, वो लफ्ज़ गुरूर अरबी बहुत ज़बरदस्त ज़बान है। गुरूर जो है वो गरर से है। गरर कहते हैं धोखे को, यानी आदमी जो गुरूर कर रहा है तो वो धोखे में है, यानी ही ओवर एस्टिमेट्स हिज ओन कैपेसिटीज़। वरना देयर इज़ नो पॉसिबिलिटी फॉर अ मैन टू हैव pride because he is nothing. Oh Allah, make useful for me what you have taught me and teach me knowledge that will be useful to me. Allahumma anfa'ni bima 'allamtani wa 'allamni ma yanfa'uni. And now this is a difference from Western idea that all knowledge is equally useful, because this is actually Prophet sallallahu alaihi wasallam has said that there is useful knowledge which he has asked for, and he has asked protection from useless knowledge. So there are many kinds of knowledge which are useless, and unfortunately in the Western education lots of things you are taught are just completely useless, and that's why it has a very bad effect. So today we are going to go over basic standard statistical inference in conventional models. This is just the basic ABC. There's lots more complicated stuff, but we must understand the first steps before we can go to the more complex. So basically from the last lecture we have unknown parameter. In last lecture it was 62%. That was the number of people who were voting for Roosevelt, but unknown to the statistician. So a statistician takes a random sample which is a binomial random variable with 50 observations and 62% success probability. And so what does he learn about theta? Remember one thing that's very important, I keep emphasizing because it keeps being forgotten. S is binomial before drawing the sample, pre-experimentally. After the sample is taken, there is no randomness. S becomes a fixed number. So this pre-experimental and post-experimental, this is completely confused in almost any treatment. So this is a source of major problems in understanding probability and statistics, that you confuse the pre-experimental situation with the post-experimental situation. So now theta is theta is unknown. I do an experiment is the sample, and I take S, which is binomial. Then post-experiment S becomes a fixed number, which is 28. So now what do I know about theta? Well, on the basis of very simple idea that the sample is like the population. So if the proportion of voters in the sample is 28 over 50, that is 56%, then I would say that, okay, my guess is that theta will be 56%. So this 56% is your estimator of theta. Now the question is, how accurate is this estimate? So this is the basic question of statistical inference. Guess anybody can make. Yani, if I ask anybody who's intelligent and knows about Pakistan, he will say, oh, my guess is that there will be 60% votes for Nawaz Sharif, for example. So the statistician is also, if he is just making a guess, then he is no different from anybody else, whether he has done random sample or not. So the key is to be able to make precise statements about the difference between your estimate and the true parameter, precise probability statements. That's what makes it different. The statistician's guess, which is an estimate, is different from an ordinary guess, because you can do some calculations which show that what is the expected error, and that is something you cannot do with the layman's guess. So first we do a little bit of technical background. For any random variable, what is a random variable? A random variable is a choice from among numbers. For example, S in the last page is a random variable. It takes values from 0 to 50 according to fixed probabilities, which are the binomial probabilities, which we have discussed. And we have seen in the last lecture what the probabilities are. So any random variable is like that. It takes a finite number of outcomes, and each outcome has a fixed probability. That's what a random variable is. Now, expected value of x, this is a technical concept. And again, like in the case of random, there is an English meaning of expected and there is a technical meaning. And these two are completely different. And there are many paradoxes which are created by confusing these two meanings. So in the English language, the expected means something that you expect, something that might happen. But if you take a random dice roll and you calculate its expected value, it takes on the values 1, 2, 3, 4, 5, and 6 with equal probability. So what's the expected value? What is the expected value of a dice roll? 1, 2, 3, 4, 5, 6, all with equal probability. No. Huh? Kya? What is this? I want the number. Right? Huh? 3.5. 1, 2, 3 on one side, 4, 5, 6 on the other. In the middle you have 3.5. So when you roll the dice, can you expect to see 3.5? No. That's why the mathematical meaning is different from the expected, from the technical meaning. So expectation is just you take every outcome, you multiply by the probability, and you add all of it. It's very simple. So this is the definition in the formula. S has possible outcomes 0, 1, 2 up to n. That is the binomial random variable. So the expected value of S is every outcome times its probability added. And as I will show later, this probability is equal to n times p. N is the number of possible outcomes and p is the probability of success. It makes a lot of intuitive sense. To actually calculate this, you can do it from this formula, but it's quite a job mathematically. You have to cancel some factorials and do some mathematical tricks, and then you can prove it. Now the thing that I want to emphasize is that the expected value, like the probability, is a pre-experimental concept. It doesn't exist after the experiment is done. And it's all pre-experimental concepts deal with many possibilities which might happen, which actually don't. Just like the probability, it says that it might happen that S is 0, it might happen that S is 1. Actually, only one thing will happen. Not all of those things can happen. So similarly, the expected value says, okay, in one world, the outcome will be 0, and the probability of that world is such and such. Multiply that and take that into your pocket. And then take another possibility and calculate its value and then the probability. So if the probability is low, then that number is discounted. And if the probability is high, then that number is counted highly. So it's a weighted average of a number of outcomes. The weights sum to 1, and the high weights are placed on those outcomes which are more likely, and the low weights are placed on the outcomes which are less likely. So this is sort of a imaginary expected value of what might happen next. But actually only one thing will happen, and that thing will happen with, once it happens, it will be 100%. And all of the other things will disappear because they were possibilities, but they did not materialize. So expectation is a pre-experimental concept. Now when you actually do a number of samples and you do the experiment repeatedly, then you make lots of observations. So those will take on different possibilities, and actually the thing is that in the post-experimental situation, the average of the observations, which is the sample average, will tend to come close to the theoretical expectation. So all of statistics is about matching the post-experimental ideas to the pre-experimental ideas. So the expectation of x is also called the mean, or the mean value, or the expected value. These are all commonly used names. As opposed to this, the post-experimental concept is the sample average or the sample mean. So those two are, and so basically the law of large numbers says that in large samples, the sample mean is very close to the expected value. This is also called the population mean, because you have a population and you have a sample. The sample represents the population. So the sample mean converges to the population mean in large samples. Okay. Now the variance is the expected value of the squared deviation from the mean. So you take an observation, the deviation from the mean is the difference between the observation and the mean value, and then you square it to get rid of the sign, and then you say what is the average value of this. Again, this is pre-experimental concept. So you you average this over all possible outcomes, and you find the average, and that's called the variance of the random variable. Variance is a very important theoretical concept. So if S is binomial, as we are working with, the variance of S is the expected value of S minus the mean, which is NP, as I have said, and the square of that. So you take the square of S, you take S, subtract the mean, square that, and then you take the average of this over all possible outcomes. This is a pre-experimental. So now, theorem is that if S is binomial, expected value of S is NP, and the variance of S is N times P times 1 minus P. And we will prove this shortly. Not because the proof is important, but because these are some theoretical properties of mean and variance which we all need to know. These are used all the time in probability and statistic calculations. So the first thing is that the expectation is a linear operator. So if you have the sum of random variables, the expected value of the sum is the sum of the expected values. And this is true for all random variables. Yani it doesn't require independence, unlike the second law which requires independence. So now remember, what is S? S is B1 plus B2. It's the sum of Bernoulli trials. Each Bernoulli trial has success probability of 1 with probability P and 0 with 1 minus P. So if I want to take the expected value of S, it's just the expected value of B1 plus B2 plus up to Bn. And I can spread the expectation out by the linear property. So expected value of this sum is the sum of the expected values. Now for each B Bernoulli trial, it's easy to calculate the expected value. There are just two outcomes. One has probability P, so it's P times 1 plus 0 times 1 minus P. So 0, of course, disappears, so it's just P. So for every Bernoulli trial, the expected value is P, the probability of success, which makes perfect sense. I mean, you should understand this intuitively also, that you have a trial in which you are going to take 1 will occur with probability P and 0 will occur with probability 1 minus P. So on the average, about P% of the time, 1 will occur. So the average value, the mean value is P. So that's for 1. Now we have the sum of n of these trials, so it's n times P. Very simple. And this also corresponds to our intuition that if we have a P% probability of success on one trial, how many successes will be there in n trials? Well, it's just P% of n. That's natural. Okay, so now the variance is a more complicated concept, but the variance of a sum of variables is also the sum of variances if the variables are independent. So variance is also linear, but not like expectation. Expectation is linear without any condition of independence. But variance is linear if the variables are independent. Here we have sequence of Bernoulli trials which are all independent. So the variance of the sum is the sum of the variances. So from that then it becomes easy to calculate the variance of the S, because for one trial we can calculate it easily. There are only two possible outcomes. One possible outcome is 1. So we subtract the mean, 1 minus p, square it, it's 1 minus p squared, and multiply by p. The other possible outcome is 0. So we subtract the mean, 0 minus p, square it, and again multiply by the probability, which is 1 minus p. So it's just very simple algebra. The variance of B1 becomes just p times 1 minus p. There's some cancellation which occurs. And so p times 1 minus p is the variance of one trial. And so if you have n trials, it's just n times that. So n times p times 1 minus p is the variance of S. Again, this can be calculated in other ways, but other ways are much more complicated. Okay. So the reason that we calculate the mean and the variance is because of the central limit theorem, which allows us to approximate the binomial by a normal. And basically, the central limit theorem says that the binomial is approximately normal for large n. Very simple. The binomial distribution is the same as the normal distribution. Now, the normal distribution is characterized by two parameters, the mean and the variance. So, if I take a normal distribution which has matching mean and matching variance, then that normal distribution will be approximately the same as the binomial. So that's what the central limit theorem says. So now I have the binomial has variance, has mean np, and the variance is n times p times 1 minus p. So the central limit theorem says that the binomial np distribution is the same as, approximately the same as normal with mean np and variance n times p times 1 minus p. So that's it. That's the central limit theorem. Now, if we want to apply this theorem, then there is something we need to do, which is called standardization. And this we will discuss in much greater detail when we study the normal distribution. Right now I'm studying the binomial beta distribution, which is one of our basic models. The second basic model is normal. And that is the most important and most widely used model. But the binomial beta is much simpler and easier to understand. So I will cover these normal concepts in detail later on when we study the normal distribution. But right now I just use something very simple. Suppose x is normal with mean m and variance v. Define z equals x minus the mean. This step is called centering. Whenever you take a random variable and you subtract the mean, that centers the random variable. It gets rid of the mean. Now the new variable has mean 0. So subtract the mean to center it, and then divide by the square root of variance. The square root of variance is the standard error by definition. Standard error of any random variable is the square root of the variance of that random variable. So subtract the mean, divide by the standard error, then z will be normal with mean 0 and variance 1. This is called the standard normal distribution. So basically, if I have a normal with different mean and different variance, subtracting the mean and dividing by the standard error makes it into a standard normal variable. This is crucial. So now, in classical theory, all inference is done by using something which is called a pivotal statistic. A pivotal statistic has the property that you know its distribution. It doesn't depend on any unknown parameters. That's the key property of the pivotal statistic. Now the S that we are working with is normal with mean np and variance np times 1 minus p. P is unknown parameter, so this is not pivotal, so we cannot do inference with that. But if I subtract np and divide by square root of np 1 minus p, then the distribution is, according to the central limit theorem, approximately normal. And so S minus np divided by square root of np 1 minus p is a pivotal statistic because it has no unknown parameters. When it has no unknown parameters, then I can make probability statements about it. So the standard statement that we will use is that probability that z is between -2 and +2 is 95%. Actually, you know that it's -1.96 and +1.96. But in practical situations, this difference is unimportant. Yani, the difference of 0.04 doesn't really matter. In statistics and probability, we are always doing rough calculations. So it's very important to keep to the level of roughness. If you put in 1.96, it gives the illusion, the suggestion that you know things to the second decimal place where you don't. There's too much randomness and too much error going on to be able to specify to that level of accuracy. So it's better to use 2. So probability -2 less than z less than 2 is approximately 95%. We are going to make a lot of approximations. This is just one of them. And this is not going to cause us big troubles. It's important to know when an approximation is critical and when it is not. And that's also something that, a statistician is always making guesses. And so some numbers, a very small difference can make a big difference in the outcome, and some numbers, it doesn't. So this is one of those numbers where it doesn't matter what you do. But there are other numbers where the exact value is important. So now, we have a pivotal statistic, and we can make a probability statement about that. So you can see immediately that if I put in S here, S minus NP over square root of NP minus 1 minus P, then we are making a probability statement about the P, which is what we are interested in. But there is something wrong. This is true, this probability statement is true pre-experimentally, before we have the observation on S. Post-experimentally, it's no longer a probability statement. So some value of Z will be observed. For example, Z is 1.6. This is a number. And then we will say that probability of -2 is less than 1.6 is less than +2 is 95%. That's ridiculous. That's stupid. 1.6 is 1.6 and this statement is true with 100% probability. So, post-experimentally, this statement makes no sense. Pre-experimentally, it's a valid statement. So, now our estimate of P is P hat, which is S over N, the proportion of successes in the total sample, and the probability absolute Z less than 2, 95%, means that pre-experimentally, I'm just doing the calculations here in this slide, that S minus NP over square root of NP1 minus P is between -2 and +2, which means that S minus NP is less than, absolute value is less than 2 times the square root of the variance. And that means that the difference, if I divide both sides by n, difference between P hat and P is bounded by 2 times the square root of P times 1 minus P divided by the square root of n. This is true with, this bound is true with the 95% probability. Now, one thing important to note here is that n is in the denominator. So, as n goes to infinity, we will get more and more accurate bound. The difference between P hat and P will be becoming smaller. But one more thing is that the square root of n goes down quite slowly. That is, suppose you have a sample of size 100, this will give us some standard error, or whatever it is, we'll calculate, like 16% for example. Then, if I want to reduce from 0.16 to 0.08, I want to make the standard error half, I have to quadruple the sample size because of the square root. So going from 100 to 400 will make my standard error half of what it was. So this is important because very quickly the n becomes very large. If you want to try to get very tight standard errors, which is what we want to do, we want to get an accurate estimate, but because of the square root, you get huge sample sizes very quickly. So you have to settle for some reasonable inaccuracy. You cannot make the accuracy very precise without increasing the sample size by an enormous amount. Another thing is that all of this is, this is not a perfect bound. This is with 95% probability. So I can increase the probability, but I can never get rid of it. So in the end, we are always making guesses. We can say that okay, p hat and p are probably with 95% probability different by only about 16%. But this can never be a certainty. This is not a tight bound as it would be in mathematics. So that's again the difference between mathematics and statistics. So now there are two big problems with this. This is the basics for the statistical inference, but there are two big problems. I mean, basically the statement that we would make in conventional inference is that p hat minus p are close to each other with 95% probability, and their difference is 2 times the square root of p times 1 minus p divided by the square root of n. But there are two problems with making this statement. One is that it's true only pre-experimentally, and I want to use it post-experimentally. And the other is that the p is what we are trying to estimate, so it's unknown. So the bound that we are trying to give cannot be calculated. So there are two big problems with trying to do conventional inference using pivotal statistic here. So we've solved these two problems. The easier problem is the unknown bound, the unknown p. Again, it turns out that if I use p hat, this is called bootstrapping. There's a number I don't know, and I'm trying to estimate, and I use my estimate for that number in the bound side. So square root of p times 1 minus p is estimated by square root of p hat times 1 minus p hat. Now this seems like an illegitimate maneuver because p is what I'm trying to estimate. So if I know p, then the whole thing is useless. So if I'm saying that p hat equals p, then what's the point of all this calculation? Then I just say, okay, p hat is equal to p hat is 56%, so p is 56%, finished. No need of all of this calculation. And that's what bootstrapping means. Bootstrapping, the phrase bootstrapping refers to the English proverb that pulling yourself up by your bootstraps. You take your bootstrap and you pull yourself up. Obviously, it cannot be done. So this is what we are doing. We are doing something illegitimate, but it turns out that in this case it works. The standard error does not change a lot. So if you estimate the standard error by this number, 0.56 and 0.54, even if you change the 0.56 to 0.6, this number will not change very much. So the fact that p hat is only an imprecise estimate of p does not cause much change in the number on this right hand side. So it's not sensitive. If this number was sensitive, then we would not be able to use the bootstrap. But in this particular case, the bootstrap never works always. It works in very specific cases. You have to know, is it going to work? And this is just a matter of experience, that we know from experience that in this particular case, replacing the p by p hat doesn't cause much problem. So we do that and we say, okay, p hat minus p are going to be less than 2 times the square root of 0.56 times 0.44 divided by the square root of 50, and I do the calculations, it comes out 14%. So what this tells me is that with 95% probability, the difference between my estimator, which is 56%, and the true value, which I don't know, is less than 14%. Now, so the probability statement. So now we come back to problem number 1, which is even more difficult, more problematic. So technically, I can say that my estimator is 56%. So I subtract 14 from it, and I get 42%. And I add 14 to it, I get 70%. And I say, okay, the confidence interval is 42% to 70%, and I can say with 95% probability that P is going to lie between these two values. But this is not true. This is not true because this would be true pre-experimentally. But pre-experimentally we cannot get here because I'm using the actual observed value of the P hat, 56%, to make this calculation. That's a post-experimental calculation. So I can't have both. If I'm in pre-experimental situation, I don't know P hat. If I'm in post-experimental, I don't have probability. So what we do is we'll do a little trick. We say, okay, instead of saying probability, I'll say confidence. So I say that with 95% confidence, P is between 42% and 70%. Now, the fact is that P is either in here or it is not. It's 100% true, one way or the other way. The only thing is that I don't know which one is true. And so subjectively, it might be true that my own ignorance or my knowledge, the state of my knowledge about P, can be reflected by this statement that probably, so that's why the word confidence is used, because confidence is a state of the mind. It is not an objective state about the real world. So I am reflecting that because I don't know P, when I have observed 56%, then I can feel, and this is just a feeling, with 95% confidence that probably the true value of P is between 42% and 70%. But it is not an objective statement about the real world. It is a statement about my feelings. So, for example, in the particular case that we are working with, P is actually 62%, so this is 100% true. There is no chance of it being false. But if I don't know that the value of P is 62%, then I might think that I might have 95% confidence. So these are the two problems with the conventional inference, and that is how they are solved. One problem is solved by bootstrapping, and the other problem is solved by replacing probability statement by confidence statement. There is also an interpretation of the confidence statement that if I keep making in the pre-experiment, in the post-experiment, I keep making these statements. So 95% of my statements will be true, and 5% of my statements will be false, which is different from the probability of the event itself. The event itself is not random, but the truth or falsity of my statement is. Okay, so that's your 95% confidence interval, and that is the solution. So if you ask a conventional frequentist, a probability theorist, that what is the solution to the problem of inference, this is the solution. So we will say that P hat minus P is between plus or minus 2 standard deviations, and 2 standard deviations are calculated by bootstrapping. So I can say that P hat, for a sample size 50, the error is within plus or minus 14%. If I want to reduce the error to 7%, I will have to go to a sample of 400. If I want to reduce to 3.5%, I will have to go to 1600. Now at 3.5% I am getting there. 3.5% is good because if my 56% is accurate, then I want a confidence interval which is only on one side of 50, right? Because then I can predict the outcome. In the current situation, with my sample of 50, my interval is 42% to 70%. So I don't know who's going to win, because from 42% to 50% is also part of the interval. So I want to have an interval which is small enough that I can exclude. Now the thing is that you cannot tell the sample size in advance, because you don't know. Initially, before you have done any sample, you don't have any knowledge of the probability. So often what we do is 2-stage sampling. So in the first stage, I determine the value of P like this, which is an approximate value, which is 56%. Now I say that, okay, if within plus or minus 3.5% I can get a sample of size 1600, then I will be able to predict. So I take this 1600. Now this 1600 is not accurate because it's based on the assumption that P equals 56%. If the true value of P is 56%, then a sample of 1600 will give us a 95% confidence interval, which lies only on one side of 50. So I will be able to predict the election. But actually, the true value could be 52. If the true value is 52, then I will need a much bigger sample to make a small interval which is on one side of 50. So this is one standard problem. Okay, so one of the inferences is the confidence interval. The other inference, which is exactly parallel to this, is called the significance test. So if I have a null hypothesis is that P is less than or equal to 50%. So if this null hypothesis is within my confidence interval, then I will not be able to reject it. If it is outside, then I will be able to reject it. So actually both of these things are the same. The confidence interval and the hypothesis test, they have basically the same structure. So from 42% to 70% is my confidence, 95% confidence interval. That means that any value of P outside this can be rejected at the 95% confidence level or 95% significance level, and any value inside 42% and 70% we will not be able to reject that null hypothesis. Now 95% is sometimes not enough. You need 99%. So that's very simple. You go from 2 to 2.6, which is the 99% cutoff point for the binomial, for the normal. Or if you want to go to 90%, that goes to 1.6 or something like that. Yeah, something like that, 1.65, yeah. So anyway, so you can get different types of confidence intervals by changing the number, but the rest of the theory is the same. So it's basically straightforward. So we get the confidence, and this is the whole picture of conventional inference with respect to the survey in very simple model. Now the complications arise when your model is not a simple random sample, when you have, and no model, in real world, you don't have census with simple random samples. You have stratified sampling and proportional sampling. So then your basic model is much more complicated. It's not a simple binomial anymore, and so things become more complicated. But basically, in the end, we end up with something like this. But to get to this place requires many more steps. Okay, so we just illustrate, just to make sure that one thing that is very important to understand in the process of learning, that at all times we work with two things. One is the particular, special, concrete case, and the other is the general law. You have to have both of these things in mind at the same time. The problem with the standard method is you do a theorem and a proof which is all abstract, and you never translate it into concrete practical terms what it means. You don't understand the theorem unless you can understand. At the same time, just understanding a lot of concrete examples doesn't give you the pattern which is the theorem. So you have to have both. You have to have the theorem and you have to simultaneously understand both things in order to understand what is going on. And it is never developed. And this is something you have to practice very hard. Here is a law. What does it mean when translated into concrete terms? Here is a set of concrete facts. What is the law which governs all of these concrete facts? Both of these things you have to go from one step to the other step, and that is what generates understanding. And failure to do this in teaching is what generates complete misunderstanding, which is what I see every day. That is, people have understanding of the theorem and the proof, but no idea how to use it, or they understand a concrete fact, but they don't see that it is part of a general pattern. So here we have discussed the general principles of inference. Now I'm going to show how it works in a very specific, special, real-world example. And when you know both of these things, then you will understand what is going on. So here we have already discussed in the US elections in 1936. Oh no, I've taken a different case. So in the Pakistani elections in just recently, 2013 or something, there were 46 million votes were cast. So suppose I take a random sample of 250 voters out of this 460 million. As you know from our previous lesson, this sample is not too small. If I do a good job of randomizing, this will be good enough. But normally we cannot do a good job of randomizing, so we need a larger sample. So anyway, I take a random sample and I find that in this sample, 100 people are voting for Nawaz Sharif. So now the question is, how many votes will be cast for Nawaz Sharif in the real election, which is to take place later, where there will be 46 million voters. So my p hat is 100 divided by 250, which is 40%. So now I have to construct my confidence interval. So square root of p hat times 1 minus p hat is square root of 0.4 times 0.6, and that is 0.49. So 95% confidence interval is that p minus the true number of votes cast minus 40% will be within 2 times 0.49, that's square root of p hat minus 1 minus p hat, divided by the square root of n, which is square root of 250, and that comes out to 6.2%. So I can say that 40 minus 6.2 is 33.8, and 40 plus 6.2 is 46.2. I've written the wrong number here. So basically, my 95% confidence interval for the number of votes that are going to be cast for Nawaz Sharif is that it will be between 33.8% and 45.2%. That is the end of the part 1 of this lecture.